So, this is a very, sometimes we can't solve first order differential equations, but you can always plug them into a tool like p-plane, and you can analyze what they look like. Because geometrically, you can see different traits of the differential equation. Of course, if you think about it, you've got dy dx equals to a function, right? So that already tells you all kinds of things geometrically, because dy dx, after all, is the slope of any solution to that function. So there's a direct geometric approach you can take to differential equations, which is useful for analysis of possible solutions, geometry, let's say. Of course, you can reverse engineer that to make a differential equation which has geometric features that you'd like as well. That's what I did with this example. It's kind of a backwards example. It's also useful to, the other standard problem I ask in differential equations, and even in calculus 2, of course, is the problem of orthogonal trajectories. Given a web of solutions, you can ask, what's another family of curves which meets that given family of curves perpendicularly wherever they meet, right? These would be called orthogonal trajectories. And so like here, I say find the orthogonal trajectories of x squared minus y squared equals to 1. Well, that's a specific curve, right? That's actually a particular hyperbola. But I explain in the notes a very systematic way to take the differential equation for your given set of curves. And, so if this is the differential equation for the hyperbola, then the orthogonal trajectories will have minus the slope, minus the reciprocal of the slope, right? M goes to slope minus 1 over m for the perpendicular line. So I just do minus 1 over x over y, which is minus y over x. You can separate that and solve it. You get just lines through the, you get the reciprocal functions, which we know from our study in linear algebra are rotated hyperbolas yet again. But anyway, it looks something like that. Now, so I spend some time in the notes to really try to give you a couple different ways of looking at orthogonal trajectories, directly from the dy dx viewpoint, but also from the Pfaffian viewpoint, the m dx plus m dy. I show you how you can just take m and n and flip them to something new to get an orthogonal trajectory. It's useful to be able to think at both levels. Here's a bit on physics. Let's read it. There's, of course, salt mixing tank problems, and here's a population growth problem. Talk about carrying capacity, all kinds of fancy stuff. Here's a fun one. In 1920, a paper by R.L. Pearl and L.J. Reed found that P of t was 210 divided by 1 plus 51.5 e to the minus 0.03 t, where these are millions. And t was the time and the number of years past 1790. It does pretty well in 1950, where it well approximates the population of 151 million. But the carrying capacity of 210 million for the U.S., it turns out not to be correct. So, I mean, and I don't know, population growth, well, I have my views. You can find the terminal velocity of a raindrop here. Here's a more complicated version that I don't know if I entirely believe in. No one's really checked that very carefully yet. You can talk about rockets, talk about flexible rope falling. I mean, the applications here they're much more complicated problems than we could have hoped to solve in regular physics course. And so you should look at those and appreciate what we can do. This section I'm proud of. Here I really try to connect, as you look at m dx plus m dy versus, there's like a vector field that corresponds to the differential equation. So I'm trying to make a connection between the vector field corresponding to m dx plus m dy and the vector field itself, and try to plot it and understand it. That's what this section is partly about. This is called the slope field. So the given differential equation, x dy plus y dx, these would be like little lines that have slope dy dx, because it's defined by the differential equation, and then the blue, of course, is a solution set. And so I have a whole section. This is how we can visualize differential equation. Obviously, I don't like to ask these on tests just because it's really, really hard to create them and or grade them. But you can start to appreciate the richness which is possible in the solutions to first-order differential equations. Certainly, it's not true that the sum of solutions is again a solution. It does seem to be generically true that if you take the totality of all solutions, they fill out the plane. they foliate the plane. Through each point, it seems like usually there's just one solution. However, there's these kind of points here where it looks like there's more than one solution that goes through, right? You don't really fully scratch that itch until you get to graduate ODEs. And finally, here's one of my favorite examples. This one, Michael Shumate showed in his recent honors thesis how you can solve this by making a polar coordinate substitution. It has a rotational symmetry this differential equation does. As you can see from the solution set, I love this differential equation, it's really cool. Finally, last but not least, the existence of solution theorems. There are existence theorems for first order ODEs. Basically, they say that if you have the little f, dy dx is like the little f, if you have that the little f is continuous on a rectangle, there's at least one solution for each point in the rectangle. That's one theorem. If you have that the little f is continuous on some rectangle and that derivative with respect to y is not equal to 0 at some point, then you get a unique solution near that point. And so that's always in the backdrop of everything we're doing. Here's a nice one. The plot, the software puts little red dots for points which are outside the domain of definition for the differential equation. Anyway, I asked some subtle questions about this in the mission that will push you a little bit further into this concept discussion. Certainly, one of the weaknesses of our course is a lack of serious thinking about existence and uniqueness. That's the next level of inquiry. Mostly this is about computation in here, what I'm doing. So with that, we'll take a break and then we'll start again with the ordinary n-order problem, where we will use linear algebra with vengeance, as you shall see. Oh, I better not show that. I really do need to take a break.